We have a problem regarding the helical ties. Okay, only thing is that the initial portion remains the same. That is how to find the cross-sectional area and how to find the longitudinal area of longitudinal steels. There is slight difference, but majority of the portions remains the same. So we will see how to do this. So in this case, we are taking a design problem again. Design a short axially loaded circular column having helical tie reinforcement to carry a service load of 1000 kilonewton. Similar question as what we have done now. So again, we have to carry a service load of 1000 kilonewton, and we are supposed to use M20 grade concrete and Fe415 grade steel. So let's see what we have difference here. So first thing is that I have already explained that when we provide a helical ties, means ties in the form of helix, what we have is the main advantage is that this column will be able to carry additional load. So basically we will assume that the columns with helical ties will be able to take up 5% additional load than a similar column which have say ring type or any other type of this ties. Okay, so basically, if we are again sticking on to the equation that we use for axially loaded column, that is Pu is equal to 0.4 times FCK into that equation. In that, Pu will represent 1.05 times that value. That is, suppose I am getting the design. Suppose I am saying you that the design strength of my column is something like 1000 kilonewton. Say in comparison to a similar column where we don't have helical reinforcement, this value 1000 kilonewton will be equal to 1.05 times of the Pu corresponding to a similar column without helical reinforcement. Say let's take two examples. First one is not having helical reinforcement, instead they have normal ties. Second one is having the same diameter circular column, cross section is same, longitudinal reinforcement is same, other things are all other things are same. Only difference is that the ties is in the form of helical reinforcement. So basically this second column will be having a Pu which is 5% greater than the Pu of the first one. That is, the Pu of the second column will be equal to 1.05 times the Pu of my first column. That is what first thing that you have to understand. So basically in this question they have given a service load as 1000 kilonewton. So this is the load that should be carried by this column. Okay, so first thing that we will do is that we will multiply this 1000 into 1.5 so that we will get the factored load. Okay, so in order to substitute the load carrying capacity for normal columns, what we have to do? We have to divide this by 1.05 times. So we will get the load carrying capacity corresponding to a normal column. So since we have helical reinforcement for this factored load, we have to divide that by 1.05 times. Okay, so we will get the Pu value, and in the equation we have to substitute this Pu, then find out the dimensions and other things. Afterwards, in the later stage, we will provide the helical reinforcement which will take care of this division. Okay, we have reduced the load by not reduced, we have actually divided this load by 1.05, and we are substituting this value here and finally finding out a diameter with respect to that. And in a later stage, to compensate this, what we will do, we will provide the helical reinforcement. So the first change is here, we are considering 1.05 times the strength to a similar member when we have this helical ties. So the service load multiplied by 1.5 will give us the design load, and that divided by 1.05 times will give you the load requirement for our current column. Okay, so in this case it is coming around 1428.57 kilonewtons, that into 10 to the power 3. Again, the other things remain same. The minimum eccentricity is 20 millimeter, and 0.05 times D is assumed to be larger than the 20 millimeters. Then we are assuming that we will be providing 1% steel, 1% of the cross section as steel in this case also. Okay, those things remain same, what we have seen in the previous problem. So now you substitute this Pu value here and convert that into newtons. That is equal to 0.4 times FCK, that is 20. Again, Ag, A gross minus 0.01 Ag, because we have assumed 1% steel here plus 0.67 into Fy into again the area of steel, that is 0.01 times A gross. So from this you will get the value of A gross, And since this is a circular column, you can just pi by 4 into d square will be equal to this value. From that, you can calculate the value of d. Okay, pi by 4 into a d square is equal to pi by 4 into d square is equal to 133,505. From that, you just find out the d, and here they have mentioned it as 412.3 millimeters. That is what they are obtaining. So we are rounding it up. Since this is the diameter, we have to round it up. So provide an overall diameter of d is equal to 420 millimeters. Okay. So from 412 to 0.3, we have rounded up to 420 millimeters. Now we are again checking 0.05 d is equal to 0.05 into 420, that is 21, which is satisfying our condition. Actually, this check must be done in our previous problems also. Anyway, you please understand that we have to at the later stage, towards the end, we have to ensure that this condition is satisfied, because in the initial stage we are just merely assuming that this 0.05 d will be greater than 20 millimeters. So here they have just cross verified that and found that it is true. Okay, based on the diameter which we have provided now. Now, once that is done, we know that 1% of steel is provided. So 0.01 multiplied by this cross section. Actually, it should be, yeah, they have taken 133,505. Please note here 133,505, which was equal to the area of a cross section of a circle having diameter 412.3. Again, the reason seems the same which we have seen in the previous problem. As per code, even though we are providing an additional gross cross-sectional area while calculating steel, we have to make the calculations based on the area which is just sufficient. Okay, so that is the reason 0.01 into 133,505, which will give you 1335.1 millimeter square. Now we are just assuming that we will provide, say we are checking, we will provide 16 millimeter diameter bars. So the area of 116 millimeter diameter bar is 201.06. So this total quantity divided by this will give the number of bars required, and here we are obtaining it as 6.64. So we are planning to provide 7 bars of 16 millimeter diameter, which gives a total area of this much. Okay, now provide a nominal cover. So since we are moving into the details of helical tie reinforcement, we are just coming to the actual things required. For the other cases also, when you perform a design, you have to mention how much cover should be provided and other things. For that we have a table which shows what is the minimum cover that should be provided in different environment. Okay, so anyway, here they have just provided it as 40 millimeters. Now let us use 8 millimeter diameter HYSD bar for helical reinforcement. They have just assumed the diameter of the ties to be 8 millimeters. Okay, so till now I think. Now we have to learn some few basic terminologies, and we have to understand those things. Then only we will be able to complete this design. Okay, so please look into this slide. So if you look onto the cross section of a circular column like this, see right now we have assume this to be a circle. Okay, so we have some reinforcement provided here, which are equally spaced. There are 7 numbers. Anyway, for the time being, I'm just taking it as 5. And around this, we will be providing the tie reinforcement in a spiral form, right? Around this, you will be providing it in a spiral form. So basically, this will be your cover. Okay, this will be your cover. This we have assumed as 40 millimeters. Okay, and this is your total diameter. Okay, diameter of the column. And we have one term called as core. Core means it is actually after this cover, you will be having some concrete along with this steel here. Inside this thing, you have a portion, and this portion is called as the core of the column. So now you will see some terminologies like diameter of the core. That means it is the diameter of this inner portion. It will be the diameter of the inner portion. So we will see those things. So basically, if you see here, outside diameter of the helix. Helix means we have actually provided this tie in the form of a helix. So basically, the outer diameter of the helix means this thing will also have a thickness or a diameter, right? So basically, when you look from top, we will see a thickness for our tie also. So this thing will also have a thickness. So from this outer surface to the outer surface of this tie, what is the distance? That is the outside diameter of helix represented by dk. Okay, how can you calculate that? So you know that the total diameter provided here is 420, and on both sides we have a clear cover of 40. So basically 420 minus 2 times 40 will give you the outer diameter of my helix. Okay, and in this case it is coming as 340 millimeters. I am assuming that it is clear to you. Now, what we are doing is that AK is equal to pi by 4 into 340 square minus 1407. What can be AK? It is the area of core concrete. Okay, sometimes we have the practice of representing this like AC. That is basically the concrete coming inside this core. Okay, so inside this core means we have concrete as well as some steel. We won't be considering the ties. If we are speaking about steel, we will be talking purely about the longitudinal bar. So please visualize, we have a spiral form and we are taking just a section. So this tie will be actually there only at a single location. So that is why we are neglecting that. But longitudinal bars are sufficient, so they should be considered. So therefore, what we are doing here is that we have just found out the outside diameter of the helix. Then we are calculating the area of this helix, that is pi by 4 into this diameter, outside diameter of the helix, minus 1407, where 1407 is the total area of longitudinal bars which we have provided. So that will give you the concrete present in the core region. I am again repeating, area of core is equal to pi by 4 into outer diameter of the helix square minus the area of longitudinal reinforcement. So that will come around 89385 millimeter square. So we have found out two terms, that is, one is the diameter of the helix, then using that we have calculated the area of core concrete. Okay. Now the gross area is same thing what we have previously seen, that is this total area, this outer area. So basically it will be equal to pi by 4 into this larger diameter square. Okay, so that is what they have done here, pi by 4 into 420 square, that is coming around 138544. So we have now calculated two things. One is area of core concrete, then we have calculated the gross cross-sectional area. Okay, now we will just move on to the clauses given in the code. There we have to see something. Okay, so this was the clause corresponding to that. So we have this equation here, then compression member with helical reinforcement. So the strength of the compression member with helical reinforcement satisfying the requirement of 39.4.1, that is this thing, not that 39.4.1. so we have something here below this. So the strength of compression member with helical reinforcement satisfying the requirement of 39.4.1 shall be taken as 1.05 times the strength of similar member with lateral ties. This is what we have already explained. We have already assumed that our member is having 5% additional strength. So we have utilized this case, that is 1.05. So what we have to do? So we have to ensure that this condition is satisfied. Otherwise, this thing will go wrong. So we have already assumed that our column is having 5% extra strength. So for that, this condition given in 39.4.1 should be satisfied. So let's see what is mentioned there. So there, if you read the ratio of the volume of helical reinforcement, please note the ratio of the volume of helical reinforcement alone to the volume of core shall be less than 0.36 into A gross by area of concrete core minus 1 into FCK by Fi. Okay, this is gross area of the section, area of the core. Say here using AC, what they have represented is area of the core of the helical reinforced column measured to the outside diameter of the helix. This is the quantity that we have right now worked out as and represented that by AK for avoiding the confusion with area of concrete which we have discussed earlier. Okay, so we are representing that by AK and that represents the area of the core concrete. We have already calculated that. We have also calculated the gross cross-sectional area. Then FCK is the compressive strength of concrete and Fy is the strength of steel, that is helical reinforcement, which we are using for our ties. So basically what we have to do is that we have to find a ratio between the volume of the helical reinforcement and the volume of core concrete. Say we will take a piece having a length of say 1 units, and we will find a ratio between the volume of helical reinforcement in that to this volume, and this should not be less than this factor. Say we have a factor which is given by 0.36 into A gross by area of core minus 1 into FCK divided by Fi. So we have to calculate this factor and ensure that it is at least equal to this ratio between the volume of helical reinforcement and volume of core. That is what we are going to do. Okay, so we will come back to our presentation. So here we have already calculated the area of core. Now what we are doing is that we are just calculating that factor. So we have a ratio between the volume of helical reinforcement to volume of core, and as per the code that should not be less than a factor. So here we are assuming that is equal to this factor. So for that, first of all, we have to find out the factor. So the factor is given by 0.36 A gross divided by area of core minus 1 into FCK by Fi. Okay, Fi. Therefore, substituting the values 0.36, we know the value of area of gross cross-sectional area and area of core concrete. Substitute that and we find that this factor is coming as 0.00954. So we have initially calculated this factor and we will keep that aside. Now what I am doing is that I have to calculate the volume of my tie as well as the volume of my core concrete. So this, please focus. There can be some sort of confusion, so please focus here. Diameter D of the core up to the diameter D of the core up to the center of the helix. So earlier we have drawn a diagram. See, we have a cross section like this. Then we have some reinforcements running like this. Then we have this ties again provided as a helix, and this have some thickness. Okay, so basically what we are doing is that we are just finding out the diameter from the center of the thickness of this tie to the other side. So here also we have a center, here also we have a center. I hope you got the concept. So this diameter, so diameter D of the core up to the center of the helix is equal to 420 minus. So basically this total diameter of this cross section is 420 total diameter minus 2 times 40, that is the clear cover on both sides, 40 here, 40 here. Then minus half the diameter of our helical reinforcement. We have already assumed that we will be using 8 millimeter helical reinforcement. So half diameter here, half diameter here. So basically we will have the total 8 by 4 plus 8 by 2 plus 8 by 2, that is 8. Okay, so 420 minus 2 times 40 minus 8, that will give me 332 millimeters. Okay, so now what I am going to do is that I am just going to calculate. Say I am assuming that the pitch or the center to center distance between successive spiral is S units, S millimeters. Okay, and now I am going to calculate the volume of spiral reinforcement, which is represented by VHS per 1 millimeter length. 1 millimeter or whatever unit you want, you can take. So per here I am calculating it in terms of 1 millimeter length of the column. Say I have a column having a larger height. So in that I am just considering 1 millimeter length, and I am just assuming or going to see what will be the volume of spiral required here. Okay, so for understanding this, let's do one thing. Let's take a bigger case. Say, please look into this slide. Say I have a column having a height of say 1 meters. Okay, this is the side view of my column, and this height is 1 meters. Okay, and if you look onto this cross section, so I am just drawing only the tie. Okay, I have a simple ring like this. Okay, I have a ring like this which was kept at this location. Okay, it is not right now, it is not in the form of a helix. I am just keeping this here. Okay, so what will be the perimeter of this ring? This is now perfectly a circle. So it will be equal to, what will be the value of perimeter? It will be pi d. Okay, so basically This total length is pi d. Now what I am doing is I am just cutting it at this location. I am cutting at one of the location. Again, the perimeter remains the same. Value of perimeter is pi d, and I am keeping one end, say this end, fixed at here, and I am just pushing the other end to the top portion. I am bringing it to this part. Okay, I am keeping one end here and other end here. So what you will get is again a spiral like this. Okay, again a spiral. So please visualize that you will be getting a so not like this. So basically, when you lift this, say you will start from here. After this, you will go like this, and finally you will reach the same point. So once you complete this rotation, you will reach the same point, so that there will be only one center to center distance, because we have just lifted this ring. One end is kept at the bottom and other end is kept at the top. So this part which is at the bottom will be in line with the part which is coming at the top. So basically here we have only one center to center distance, because we are having only one circle here, and we know that this length is pi d here. Is this much clear to you? Is it clear?
Yes, sir.
Okay, now what I am doing is that I have the same column here. Okay, I have the same column here. So instead of this single ring, I have two rings now. Two rings kept on top of each other, and this is connected actually. Okay, and I am cutting one end in the same fashion, and say from this two rings, I am holding one bottom point at a position, and I am keeping the other point at the top, so that what you will get is, say you will have two complete circles like this. So basically from here I have started, I have rotated around this, and when I come here, I will finish one ring which will constitute pi d. Then again I have one more rotation like this. This will complete my second one. So basically this is 2 times pi d. The diameter is, the perimeter is double now, right? So in this case, so basically we will be having two center to center distances. In the first case, we were having only one, but here we have two center to center distance. So this is basically our S. So in this case, S was equal to 1. In this case, S will be equal to, say, if again the height is remaining same, it will be equal to 1 by 2. Is it clear? Am I right? So here I was having only a single circle, so I just expanded that. So the center to center distance will be equal to the length of the column. That is in this case 1 meter. The second case I have two circles, then I expanded that. So we have two center to center distance. This 1 meter will be divided into two parts, because we are uniformly lifting this. So this S, or this pitch, or this center to center distance will be equal to total length divided by 2. Am I right?
Yes, sir.
Right. Now in a third case, what I am doing is I have the same 1 meter, but here I have 3 rings. So what will be the center to center spacing here? So basically this will be first, this will be second, and this will be third. So in this case, this center to center spacing will be 1 by 3, because we are dividing this 1 meter into 3 equal parts. Okay. So this is one concept. Now we will see how they have calculated the volume of the spiral. So for calculating the volume of this spiral, what we will do is that we will first of all find out the cross section of this tie. The cross section of this tie will be equal to pi by 4 into diameter square. Pi by 4 into 5 square. That is what they have done here. Pi by 4 into 5 square. So that will give me the area, cross sectional area. Now I have to multiply that with the perimeter, so that I will get the total volume, basically cross section into the length or the height. So in this case, since I have a helix here, so I have to multiply the cross section with respect to the perimeter here. So if it was the first case, my center to center distance, or if it was the first case, the volume will be equal to pi by 4 into diameter of my tie square into pi d. Okay, pi by 4 into pi square into pi d will give me the volume. Okay, if it was the second case, what will be my volume? So here basically it is my volume. Okay, if it was the second case, what will be the difference? What will be the difference in that? Say in this case, I was having only second ring, means one ring, but here I have two rings. So basically, what I have to do, I have to multiply this by 2. Am I correct?
Yes, sir.
Am I correct or not? Please think and answer.
Yes, sir.
If it is a third case, what I have to do, I have 3 rings here, in which each ring is having pi d perimeter. So basically, cross section into 3 times this value. Likewise, it will be going. So if you observe here, so in order to get this effect, 2 times this x, say in the second case, I'm talking about the second case, pi by d is perimeter into the cross sectional area into 2 will give me this one. Instead of multiplying with 2, suppose I am dividing that by center to center distance. Will I be getting the same value of the volume? Please think here. Here the center to center distance was 1. Here the center to center distance is 0.5. So here pi by d divided by 0.5, which is equal to 1 by 0.5 is 2, right? So it is equivalent to 2. If it was the third case, what I will do? Pi by d divided by the center to center spacing here, that is pi by d divided by 1 by 3 or 3 times pi by d. Likewise, I can generalize it now. So what I am doing is perimeter into area of cross section divided by center to center distance will be my volume of a single spiral in 1 meters or in unit length. Is the concept clear to you? Is this concept clear to you? This is the only confusing part. The calculation of volume. Any doubts in this?
No, sir, it's clear.
Clear, right, for all? So anyway, it's already a time today. So please, if it is not clear, please try to understand this. So you please visualize one ring is kept here and you are just pushing it to 1 meters. So what will be the perimeter formed here? And how can you calculate the volume here? And move on to a second case where you have 2 rings, 3 rings. Now you just try to calculate the volume for all these three cases and try to express that in terms of center to center distance. So once this is clear, there is nothing else here. So once we calculate this volume, we will find the ratio of. So if you observe this, now we have the volume of the spiral in terms of S, where S is the center to center distance or the pitch of our tie. So finally, we will be getting a ratio like this in terms of S. And now, as per the clause, for getting 1.05 times strength, what we have to do? If we take the ratio of volume of the helix to the core volume, it should be equal to, it should not be less than this value. So basically, we are equating that to this value, 0.00954. So this is the ratio, that is 427.3 divided by S divided by 89385. That is what is done here. So you will get it as 0.5865 divided by S, and we will finally equate this to this factor, that is 0.00954 as per the code. So from this you can calculate the center to center distance required. That is how we will find out the pitch here. That is the main difference. So what we will do? We have to check the conditions for pitch. So if you refer your IS 46, I have already explained this. For helical reinforcement, we have some special things that should be checked. The pitch should not be more than 75 millimeters. That is the first condition. Nor more than 1/6 of core diameter. We have already calculated the core diameter, which was 340 millimeters. So 1/6 of 340 is 56.7 millimeters. So it should not be more than 56.7 millimeter, but we have obtained a value of 61.5 here. So that cannot be provided. Okay. So this is the second condition. Also, it should not be less than 3 times 5s, where 5s is the diameter of our helical reinforcement. 3 times 8 means it is 24. So it should not be less than this value. Okay. It should not be larger than 75 or 56.7, but again it should not be less than 25 also. Hence, we will provide a pitch equal to 55 millimeters because we cannot go with a value which is larger than 56.7. So we will stick it to 55 millimeters. Okay, and finally we have to show a detailing also. So basically on top we will be having the cross section. Then we will be having 7 reinforcement. Okay, 5, 6, 7. Okay, you just provide it uniformly distributed. After this, around this, we will be having the spiral reinforcement. So you can just show a circle around this. Then you have to show the diameter, properly mark the diameter, outer diameter. Then if you want, you can show this thing, that is the cover. What is the cover provided? So 40 millimeters. Then you have to actually show these things. Okay, so these are actually 7 nose of 60 millimeter 5. Then we have this spiral. So this is actually 8 millimeter at 55 mm C by C helical. In brackets we can helical. Okay, and also we can just show a cross section like this. So we will have a cross section. Okay, so please assume these sides to be straight. Then we have different reinforcement. You just look to the cross section and you draw the needed reinforcement. I am arbitrarily drawing this. Then we have this spiral reinforcement which is going like this. Okay, and this thing should be actually like this because there is continuation on both sides, right? And now here also you have to show. See, these are actually 16 or 7 nose of 16 millimeter 5. Then we have this one, that is 8 millimeter 5, and you can also show like this. This center to center distance is 55 millimeters, and you can also show the this outer diameter. So this is your detailing. So this will complete your problem.